In this video, I'm going to be talking about the following C++ topic. First, I will talk about trailing return type for function and function linkage, and finally I will talk about recursive function. I will use this editor with this skeleton code in it. Before I actually talk about the trailing return type, I need to talk a little bit about keyword that was introduced in C++ standard, which is called auto keyword, which is essentially which is also called as placeholder type. The reason it is called placeholder type is it can be used to hold the place of the type. For example, if I define a variable of int type x, I would be defining like this. But if I want to use I want to have some placeholder for this type, then I can use auto in this place, right? So that's the reason why it is called placeholder type. And one of the things that you should not miss when using auto keyword is you should initialize this variable to some data immediately, right? So if you don't initialize, that is going to be syntactic error. Compiler will not allow it to get compiled. The purpose of using auto keyword is actually essentially telling the compiler to infer the type of this variable x based on the data the type of the data it is initialized to. In this case, it is initialized to 25, which is integer type. So compiler will infer the type of x to be integer. In this case, 2.4 is the double type, so type of y will be inferred as double type, right? So let me move back and discuss the trailing return type. Particularly, we talk about the function. Suppose I have a function to add two numbers, and it returns addition of a and b. The way we use the trailing return type is we actually ask the compiler to infer the return type by putting auto keyword in this place, and we need to specify the type to be inferred in this place, in this case int. So compiler will scan this function and let me see why it is error here. Okay, let me use sum1. So compiler will actually put aside this return type and then continue scanning the function, and then at this point compiler should have information that is sufficient to determine the type up to this point. So now in this case we have mentioned this explicitly, but in many cases, in actual situation where we want to have the type, then we don't mention the type exactly like this. We have an expression, and we want compiler to determine the type. For example, in this case the return type is going to be a plus b, so the type of the return data is going to be a plus b, summation a and b, and then the type we want the compiler to determine would be through this operation called DCL type. Just let me a plus b. So now compiler will actually would have already scanned the type of a and b, and then it has sufficient information to determine the type of a and b at this point. So it will determine the type of a and b to be integer type, because the summation of two integer number is going to be integer. So it will use this and it will actually set this as a type of the function, right? So there are three key situations where the use of this trailing return type can be useful. One situation is if the return expression is very complicated, right? For example, in this case, let's say I have integer type and double and character C, right, and something else, let's say and I actually return the addition of all these things, right? So a string type, this character is not directly cannot be added to a string type, so you have to do something. We can put it something like this. So this kind of complicated expression is there, and it's difficult for you to determine the exact type of this entire expression. In that case, you can put entire expression here. Let me just remove this string type for the sake of explanation. So I'm gonna be using this expression C plus, let's say, plus D plus 22L plus 44LL. So you have this kind of expression, then sometimes it can get complicated or maybe arduous for you to determine type of the expression. Then in that case you can put entire expression in this place, then it will actually compiler will determine based on the expression. It will not evaluate the expression itself, but it will look into the type of all the things, and then it will determine the type of entire expression and use that as a return type of the function. So first situation is if expression to be evaluated to compute is, so if the expression to be evaluated to compute return data is very complicated, in that case this use of trailing return type is useful. Second situation where we want to use a trailing return type is if a variable is not known to the scope before the parameter types scan. For example, if the variable used in this expression is not known at this point, because compiler starts scanning these things from left to right, so it scans this type, but you don't know the type. So after the type, the compiler, the type nature of the variable or the thing that is in the parameter list gets accessible, then compiler will be able to determine the type, right? One situation is if you have a class, and in the class you have a type defined inside the class, right? So we have innovation thing here. Then if the function, you have a function which actually returns the ticket type, if the function is to return ticket type, then if I attempt to define this function outside the class here in this place, and I need to give the name of the class. Let me have class A is the name. So if I have this situation, then the compiler is not aware of this type of this thing. So because it is defined inside the scope of the class, so once it actually scans this class, then compiler is able to determine the type at this point. So in that case, we can ask compiler to infer, and you can have a trailing return type syntax in this case. So now this is acceptable, right? So this is the syntax. You can have other function to fill in here, other logic to fill in here, but this is the return type. So this is now it becomes acceptable, right? Again, let me show you again. If I move this ticket in this place, this is not accessible to the compiler at this point, and once the compiler scans class A and looks inside it, then the compiler knows that it is the ticket is the valid type. So you can put that type in this place. So this is the second situation. If variable used in the return expression is not known to the scope before R, right? So this is the second situation. In the third situation is the use of templates, right? So this second situation is also applies to the application of templates. In template function, let me remove this entire thing here. So in the template function, many times the return type may not be known, right? For example, if I have a template function defined like this, to type parameters, so in this case the return type may not be known. For example, based on if t happens to be both t and u happens to be integer, when you call the function like this, in that case the result of this evaluation is going to be of type integer. If I pass one integer, one double, then the result of evaluation is going to be double. So it is not known in advance. So in this situation, it is useful to let the compiler infer and the type based on the expression. For example, in this case, so now this is I mean this is probably the most the case where this trailing return type is applied mostly compared to the first two cases. May not be known in advance, so you may need to let compiler infer it. Right? So these are the three situations where we can use trailing return type. This is the syntax of trailing return type, And the first situation we want to use is if the expression is very complicated, then we want to let the compiler infer the type. And if the variable used in the return type expression is not known until these parameters are scanned, in that case okay, it should be used. And if particularly in the template function or template class, the return type may not be known until this compiler actually scans these types. In that case, you can ask compiler to infer the type, right? So you could be, I mean, you cannot use t here, you cannot use you cannot use t plus u or something, an expression in this place, or you cannot pre-assume that the return type is going to be integer type or double type or maybe long type. It could be anything. Now I'm going to be talking about function linkage. To discuss function linkage, let me use the same skeleton code. Now the thing that I want to tell you, or I want you to understand, is that the functions are linked externally by default, or they are externally by default. They have external linkage by default. Unlike variables don't have. They don't have external linkage by default, but in the function you don't need to set explicitly external linkage. I'm going to show you. I have this function, this main one .cpp, one module and another module. So I'm going to be using these two modules to demonstrate external linkage, and even I will also demonstrate internal linkage, right? So let me have a function called print hello. So I want to put I have a stream here. So I have this print hello function. If I want to use this function from this module, this main2 is one module, this main1 is another module. If I want to use that function here, I should be able to call that function, but there is a one problem, small problem. So I need to have declaration of this function, prototype of that function stated before, because compiler actually compiles these two modules independent of each other. So if I'm using this if compiling this module, it should know the syntax of the function, the signature of the function that is being used in this module. So you need to have the prototype. So with this prototype, the use of this function becomes valid, and this also gets compiled independently, and finally they are linked. When they are linked, then this module should have access to this the function defined in another module. So if I compile this, let me show you by compiling, and this should actually print this module should call this print hello function defined in another module and display it. Now let me compile this run this program. It is printing hello. You can see this is the result of the compilation and the linking, and this is the application created out of those two modules, and this hello has been displayed. So as you can see, it is linked in the main module, but I didn't have to explicitly set external linkage. You could use external keyword to set external linkage, but it is not necessary in this case. So it is linked externally by default. Right now, if I want to have this same function in this model, I want to have function with the same name in this model and this model itself, then I need to set internal linkage, right? So that is the difference between external and internal linkage. So to set internal linkage, you need to make it static. I'm not going to use print hello function. Let me create another function in the main model. The name I'm going to give is display from main1 model, main1.cpp, and I'm gonna also have the function with the same name in main2, and I'm gonna be calling this function from here. Maybe, yeah. So now I want this invocation to call only this function. Let me correct this spelling. So, and I want this invocation to call this function. So for that, if I run this program like this, it's going to be a problem. So I need to set internal linkage. I need to make sure that this is this function is visible only from in this model. Let me make change to this text printed so that we'll be able to see the difference. Now, so for that you can declare this as a static. So if I make this function static and this function static, then it will ensure that this function display function has internal linkage to main2.cpp, and this display function has internal linkage to main.cpp. One thing you should note is that first the first thing that is displayed in the output of this program is going to be the result of this invocation of this function, and in the second case it will call the print hello function, and inside print hello function you have this text printed followed by the result of invocation of this function in model 2. So let us see the output. So execution of this function, actually, first display text from this main1 model has been printed. This text, the function, that means the function display function defined in the main1 model is executed, followed by the print hello function, which actually prints the hello text, followed by the result of invocation of display function defined in main2 model. So going back to again, let me explain one more time. By declaring this as a static function in the models, you are setting this function to be internally linked to that particular model. In this case, this is a display function linked to main1 model, and this is going to be a display function linked to main to model. So whatever throughout this model, from wherever you call display function, it will actually call this definition, and in this model, from wherever you call this display function, it will actually call this function. Now I'm going to be talking about recursive function. This is going to be a little bit tricky, complicated. I'm going to try to explain make it as clear as possible. For many, it's tricky to understand, but if you spend some time, try to focus, pay attention to it, I hope you will be able to understand the content, the thing that I'm going to explain today. Now let me use the same code, make it the skeleton one more time, remove everything, all the flesh, and just leave the bone. So I'm going to talk about recursive function here. So let me begin with computing a factorial, right? So if I want to compute a factorial of a number, x equals to 10, let's say I want to pick a smaller number so that it will be easy to verify. So this is a function I want to compute. I want to ensure that this function is well defined, and it actually gets called, and it computes the factorial and copies the result in y. X result x factorial equals to y. So I want to make sure that this code runs well. So for that, I need to define a function. Obviously, if the return type is going to be integer in this case, and I'm going to have a parameter of type integer. So to compute a factorial, you can iterate, you can have a loop. So if I have the return that type, I'm going to be returning this at the end. So in between here, I'm going to have a logic for I equals to 0, I less than a, I plus plus. So you multiply I think I should begin from 1. Okay, so because I cannot multiply with 0, if I multiply with 0, everything will become 0. So begin with 1. In this case, let me quickly analyze this function just to make sure that it's okay. So if the a gets the value 0, it's going to be this result is 1. So it will start from 1, and less than condition will be not false in the beginning, so it will not get into the loop, so it will return 1. If it is 1, then it will actually run at least. No, it will not get into the loop, so it will return 1 in the case of 0 and 1. In the case of 2, it will get into the loop for one time, so it will return 2, right? So in the case of 3. So I think this should work well. Let me compile, run, and show you the output. Then I will continue. I will expand this code further to explain recursive function further. So now it is the application. I'm going to run. You can see the result. 5 factorial 5 is displayed to be 24. So if I compute the 5 factorial of 5, let me use this space itself, 5 1 times 2 times 3 times 4 times 5. I think this is not correct. So I need to make a little change in this case. Let me use the editor again. So I also need to multiply, because I think the 24 is, let me see, 1 times 2 times 3 times 4 equals to 24. So it is a factorial of 4. So for factorial of 5 I need to go up to the number. So with this I think we should I should be able to get the correct factorial value. So I'm going to be compiling this code again. So now still there is a problem. Oh, this code was not saved, so I need to save this code first, and I should try compiling afterwards. So let me compile again. Now you can see 124. This is correct factorial value. Okay. So I'm going to be getting into the getting back. Now this is the function to compute factorial, but this is not a recursive function, right? This is something called iterative logic. So we have this iteration of this loop to compute the factorial value, right? Let me change this name of the function to reflect the type of the logic that is being implemented inside. Now for recursive implementation, we need to understand first we need to understand what is recursive function. This is essentially a function which calls itself. With data. So first you call a function, and from inside the logic of that function it calls, but with the different data. It doesn't call with the same data usually, it calls with the different data. So data keeps changing, and that actually that continues the call from within the function keeps repeating for a number of times, right? So this kind of function is called recursive function. So if I want to create a recursive function, let me make a change here so that I don't see this syntactic error. So if I want to create this recursive function, then I should have a function being called from inside. So if I call from inside, then this is a recursive function. So now this is a function which the logic of the function calls itself. So factorial is a function which calls itself, but if we have a function like this and it's going to be infinite, it will be calling infinitely with, I mean, same function will call infinitely. So this sort of logic is not desired. So typically what happens is after it does invoke for a certain number of times, then there should be a way of stopping that recursion, so that this function does not get executed for infinite number of times. So that is a way of having a controlled recursion. So you need to control the recursion so that it gives you the desired output. So to control the recursion, there are two things. One is this invocation of the function itself is called recursive case, and there's another thing called base case. So in the base case, if certain condition is satisfied, then you just stop recursion. So for example, if I want to this recursion to stop, if a is less a is equals to 0, I just return it, return 1, right? If a equals to 0, I return 1. If a equals to 1, return 1. Then otherwise I return a times minus 1, right? So now this is these are the best cases. It's also possible that you can avoid this, because it's going to be, but sometimes some people want to have these two cases. Sometimes these two cases, for the sake of having efficient code, people want to prefer, but usually if we have this kind of coding, then it will continue calling function. For example, if I call this function with value 5, then it will recursively call with value 4, and then it will go inside the function again, and then that call will, it's a call again, have a recursive call with value 3 and 2 and then 1, it will return. It will never reach 0, but we need to have this case in the case we want to compute the factorial for 0. If this function is called with 0, then it will actually return 1. If it is called with other values, then it will actually, depending on, if it is 1, then it will return 1. If 2, then it will call recursively, and ultimately it will return 1. So let me show you this function works, then I will actually discuss in detail how it recursive function works. Okay, so now let me have another variable z equals to so this should this is called the recursive function, compute the factorial, and the result will be stored in z, and that is going to be displayed, right? So let me show you the output in this. So I have already compiled this. Now I need to save. I didn't save the code, so I need to save first, and then I can do the compilation. So let me do compilation one more time and run. Now you can see the first outcome was from the iterative function, and the second was from the recursive function, right? So in this particular case of calling recursive function with 5, what actually happens is, for example, in this case, let me use this space to explain. Okay, let me explain it again. In this particular case of calling the recursive function with the 5 argument value as 5, how it works is, first it will call this function with value 5, right? And inside this function invocation, a will get value 5. So a equals to 0, false, a equals to 1, false, and it will go to executing this statement. So it will return 5 times right? So it will call this function from inside. So this is the function. This invocation involves the evaluation of this statement, and this statement, before this statement is executed, you need to evaluate this expression. This expression involves multiplication of 5 times the result of the invocation of function with value 4, right? So now this function invocation will return internally 4 times 3, right? Now this is the function invocation which will actually execute this statement to return the data. Now inside this function invocation, it will return 3 times 2, because you can see a minus 1. If a is the value of the parameter, it will call with the argument a minus 1. So now again, this will execute the statement 2 times 1. Now what will happen in this invocation is it will call with the value 1 in the parameter. So it will, this statement will be true and it will return 1 in that case. So now in this case it will return 1. So now it will return 1. Now once it is returned, what happens is in this place this entire expression gets value 1, right? So now it's going to be 2 times 1 equals to 3. So this statement will return 3, and it goes back to completing the evaluation of this return statement, and this 3 will be taken by this space. Sorry, this is going to be 2, and it will return 2. Then it's going to be 6. The entire 6 is going to be returned, and it will actually, entire 6 value will actually take this space, this place. So now that execution of this return statement completes with value 6 in this place, and the result is going to be 24. And finally this return statement is going to be completed. Now this expression will get the value 24, and the result of the multiplication of 24 by 5 is going to be 120. So finally it will go back to the initial invocation, and in the initial invocation it will evaluate the entire expression to be 120, and that 120 is going to be returned from this place to this point, and that 120 is copied to Z, and that Z is actually printed by this statement, right? So this is how it this recursive invocation works. So one question that may come in your mind is looks like this iterative logic is simple, and you can perform recursion using iterative logic. Then why do we need recursion? The answer to this question is sometimes recursive logic is more natural to the problems. right? So if it is a natural, then it can lead to, which can lead to more simple and clear logic, easy to understand logic, right? The application where this recursive logic fits naturally is the in data structure and algorithm topics, including, particularly searching in trees. And one popular algorithm that you might have been aware about is tower, right? So there are many other algorithms, other cases where this recursive logic is being employed efficiently, right? So one example I want to talk about at this point is, for example, one question. Maybe you can take this as a question. If I have a function like this, I display X number of characters on the screen, so if I call this function if x equals to 0, return, and call this function from here, and I call this function from here, so what will be the output of this function? So this is one of the things that you can contemplate on, think about, right? So it is going to be displaying some kind of interesting output, so you can think about it, use this code and see what it displays, and try to understand and try to remove this part and then see what actually it displays, and try to remove this part and see what exactly it displays. I leave this discussion. I'm ending this discussion by leaving this as an exercise for you. I hope you'll enjoy this. Thank you.